Hi guys, what's up? How are you going? Today's video is gonna be English because on my current job I have to speak English all the time and I think that's a good way to improve my speaking. So this video is going to be about a concept that is often not talked as much as it should in control system, and it's a very simple concept. So let's start with a simple question. Suppose that you have an already compensated system, which is the simplest way to obtain a zero stationary error with the same transitory, right? So here's the system. I have a controller. I have a plant, and this is the controller in its factored form. This is the plant in its factored form. So we have our zeros, we have our poles, and it's the simplest way to obtain zero error, right? So think about it in a moment and come back later. Right, so uh, when we are in the control, in a control class, we are often guided to think about how can we improve this controller, right? How can we add an integrator, a game, etc., etc., right? Just because, I mean, our error is given by 1 over 1 plus kp, where kp is equal to this. Sorry. Right? Oh, sorry. So if you have, I mean, let's say some integrator here, kp is going to infinity, so this is going to 0, right? Same thing with if you have a gain here, right? If k is going to infinity, of course, this error is also going to infinity. But this is not as simple, right? Because if we uh, add some pole or add some other gain, we are probably, just probably, uh, going to change our transitory characteristics, right? So let's just think why we just, alright, we have this controller, this is good. Why don't we just make something very simple? Let's just add some gain in the feedback path, right? So what changes? So this is our closed system transfer function, right? We have this. Right? We have this thing. The first thing, our main priority is to achieve zero error, right? So how can we compute our error? Right? That's our error. Let's apply the how do we call it? It's the final value theorem. I don't know. I mean, this is just it, right? Right? It's just this, right? So this is what you have. Alright, so when the controller, the planes, they all go to 0, what you have is going to be and here we have our gains, right? Here you have our kg, or kc, and of course our k. And here, if the same thing happens, or kg or kc, and just that, right? And you want this to be 0, right? So just based on that, this exists, right? There's some value of k that this can exist, this holds, right? This is the equation that holds everything up, right? But we also want the semi-transitory characteristics, right? So we want the same poles, right? So right, and this also have to obey this, right? This have to obey this. So I mean, these cuts, and we are going to have, I mean, if we kc, kg, and then we have the productories, right? Then we have the productories that is also going to cut out, right? And this is going to be equal k, kc, kg, right? So if you think for a minute, of course this equation is impossible, but we have control over this. This is a controller. We can change the parameters over it, right? So the planes, of course, we can change the planes. So this cuts, and you have the gain of the controller is equal to the gain that we're going to add plus the gain of the controller that we can change, right? So as we can change it, I'm going to call it kc prime. I think that's how we say this thing. So, or kc prime, right? Because we can change the controller. The controller is something that's there with some easy change to make, right? So here we can also call it some prime and some prime, right? So that's the reflection that we're going to make. So for certain kc that guarantees are transitory, there is some value of k and there is some value of kc prime that stands out. These guarantees are transitory. right? So we just have to choose some value of new KC, right? And here we have a degree of freedom. We can choose a new uh, K to obtain our new error, right? Because I'm sorry, this is a plus, right? Sorry. Right? Because what's going to happen if we rewrite this equation, right? So let's grab this equation down and put it here, right here. What's going to happen is this, right? I mean, KC, this is the same thing of our original KC, right? So our denominator is the same. Right? So we have the same denominator as before, always, right? Always. And we have this degree of freedom, right? We have this degree of freedom, so we can achieve our error, right? We can achieve our error. We can achieve actually zero error always. We can achieve 2%, 3%, any error that we want, right? We can achieve just some error, right? Just depends on that. So that's the idea. I hope you guys like it. This is just the idea that when we don't have constraints, restrictions on the controller, because we always want to change or make assumptions about our direct path controller, right? But this practice grows a bias over our mind about always making controllers on the direct path, and we also can make some controller on the feedback path, right? And something sometimes better, right? Sometimes better. This is an example of just a very simple game that we can choose the error that we wanting on the system. Without change the transitory, right? So I hope you guys liked the video. That's a very generalized way to prove it. So hope you guys like, and yeah, that's it.